We have for you now one more experiment with things that electrons do or are concerned with. Mr. Coates here has a very clean plate of zinc, specially clean, and it's connected to a small gold leaf electroscope. You may be able to see the little leaves, and he's going to charge the electroscope. Mr. Coates, will it be negative or positive?
Negative.
He's going to charge the leaves with negative extra electrons, actually. Perhaps we're not supposed to know that at this stage. And he is then going to, are they beautifully apart? Yes. He's then going to turn on a naked arc lamp. No lenses, no glass, direct light. What did the leaves do? You'd like to see that probably again on a bigger scale. Let's try again. Charge up the electroscope, look at the leaves, don't worry about anything else. They're losing their electric charge of negative electricity. Something negative is coming out from them, being whipped out. In fact, they are electrons. The light is coming in like a whiplash and flinging out electrons, and away they go. Now, Mr. Coates, is it the visible light or the ultraviolet light?
Well, let's put some glass in and find out.
He'll put some glass in. You can see through the glass. It's ordinary glass, and that will let ordinary white light of all the colours go through. Nothing happens. Now take away the glass. Down they go. Is it just a mixture of stuff? Please try now with a positive charge on the leaf, on the leaves of the electroscope. It's charged again. Turn the light on. Nothing happens. Does that mean the light, the ultraviolet light, which must be what did it before, getting through the glass if it's visible, but stopping if it's ultraviolet, so it was the ultraviolet light that did it before, beyond the visible spectrum, isn't it hurling out electrons? How does it know? It certainly hurls out electrons, but the positive charge on the leaf pulls them back again, say, no, 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 you don't go out till Tuesday, and brings them back again like that. And so they're hauled back. That is something we wanted you to see. Now you'll see some other strange properties of electrons at the next lecture. We're going to talk a good deal about models, because we're reaching a stage when we have to show you models both for explaining and for understanding. And so I'm going to remind you of the kinds of model. There is a toy model. Here is a model of gas atoms. It's useful. It helps us in arguing. It helps us in explaining. And this is a thinking model, which you've seen before, of a sodium atom, quite out of date. The orbits can't be really like that, but yet it's very useful in discussing things. This large orbit miles out here says that one electron goes very far out, and so it's very easily detached in its long trip. It goes wandering out and then back, sees the headmaster, and comes back again, out, slowly wandering out, sees the headmaster, and now it'll never get back again because it's gripped away by a neighboring chlorine atom, greedy for a complete family, and making therefore a negative ion and leaving here a positive one. It's useful for our physical thinking. I'm going to talk to you today about models going right deep down into the inside of an atom. Remember that in the last lecture you saw cloud chamber pictures of alpha particles. The alpha particles going straight out, making drops of water clouds all in a straight line. They were only hurling electrons, pulling them out of rather, atoms and molecules on the way. Very seldom did one come back like that with a violent collision. That is the story of nuclear atoms until Rutherford saw alpha particles bouncing back. He didn't have the idea of any atom other than the kind that you have already been talking about, the current bun. I'm going to draw a current bun for you. There it is, and in it are embedded electrons. That was the current bun or plum pudding atom for a long time. It agreed with the fact that you could take electrons out and have an electron like that ripped out of the atom fairly easily. But when it became clear that an alpha particle could go right through atoms, that still was easy enough. There's an alpha particle. Well, it hit that electron. The worst it would do is to send it out. Another one would hit that one perhaps and pull it out and it'd go out. But even so, they would go straight through nearly all the time. And there was no chance whatever of an alpha particle here with its, we'll draw it's a big bullet with its double plus charge. There was no chance of that getting bounced back. There's too much general stuff here. This is where the mass of the whole atom was. I'm going to color it green just to make it a nice picture of it. I'm sorry, it's one of the electrons got out by mistake and rolled across the floor. There's the whole mass of the atom inside there. Its electric charge is there also, so that since it has an electric charge there, it has plus, 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 plus in among all that. You see, it is a pudding. That's why I'm quite happily drawing it like that. There's no way for this charged creature that's going across to get near enough to enough positive charge to get bounced out of his way like that. It won't happen. No. So when Rutherford and the young people working with him saw alpha particles bounced back, as they certainly did in an experiment like this, a source of alpha particles here, alpha particles coming out like this, many of them straight paths suggesting atoms are pretty hollow, and then just sometimes one bounced back. That couldn't happen without it hitting something very solid. Hollow atoms, because of this part of the story, solid nucleus. Nucleus means nut, just a little nut at the very center of the atom. Solid nucleus must be there. I'm going to show you a model to illustrate those two kinds. Mr. Coates, can we have now the, I'm going back to that, model of the two kinds. Here is a model of the old pudding atom. These are atoms here, and we're going to let a small steel ball roll down this chute, which will make a random thing. A random path for it here. We'll let it roll down and see what it does. Does it bounce back? Watch it. Went straight through. Try it again. Didn't do anything. That's just what alpha particles do, but it's not what this model is going to show about bouncing back. Ah, it knocked an electron out. There's the electron, got knocked out. Let's have a stream of them. Thank you. To my surprise, one got out to there. I don't know how it did it with this model. Most of the rest came down to here straight through, and a few electrons were detached by this stream of repulsive alpha particles, repelling a positive charge, but attractive alpha particles to an electron, pulling it out. Let's change to another model altogether. The model I spoke of a nucleus every so often. This is a bed of nails. These are tough nails sticking up here. You can see signs of the old-fashioned orbits on the pattern. Now let us roll down more. Yes, we need to clear the field of view. Wait a minute, I don't want any connection with the old establishment. Next. Lots went through, but you see those that came out to there in a fairly backwards way. This is possible now for one to be hit backwards. Look at that. And in that way, this does agree with what you see with alpha particles. So we do think there are repulsive nuclei, very small, and large open spaces, so many go right through. Thank you. I would like to illustrate that with a teaching model. This represents a nucleus here, this hat, and I'm going to roll down a launching ramp, a silver ball, and see what it will do. It bounced away, bounced back. Aim it more off-center. Aim it still more off-center. Aim it nearer to the center. Aim it off-center, and see if we can find a place where it'll just bounce back. Nope. Very sensitive. There. And now let's have a fast one. There's a teaching model of alpha particles represented by this, moving up to a nucleus and running up a hill which represents the repulsion between the nuclear charge and the alpha particles. We can show you presently models of the structure of nuclear atoms. But I have first to talk to you about it a bit, because what was the state of atomic model making when they found that they had to have a hollow atom? Here is what happened. There was a hollow atom, most of it hollow, with a nice positive charge in the center. That's the nucleus. I'll put a letter N there for the nucleus. And then far, far out, a long, long way out, were electrons, and they were out here. And when they put them, first of all, out at various distances, far out like that, a gentleman called Earnshaw had established a very clear rule that it was impossible for those electrons to rest there. They would collapse inwards under the attraction of the nucleus. No arrangement would work. So they can't be like that. And the next suggestion, and you've all heard it, I expect, is that the electrons went round in orbits. We're back with this model again. Unfortunately, if they do go round in orbits, we should expect them to give out radio waves as they go round. That's how radio waves are made, by waggling electrons to and fro. And if you have two lots of to and froing, it turns round in a circle like that. And so that too wouldn't do. And this was a sore point in the early nuclear model until Niels Bohr in Denmark comforted everybody. He made a statement which is just like the child's remark that the emperor has no clothes. He simply said, the orbits have no trouble. They stay there. They stay there. Rule 1, the orbits are stable, they will always stay there. Everybody felt quite happy about it because after that they were allowed to forget about the trouble for a bit. It was a very long time, many, many years, before this difficulty was cleared up. Why is it the electrons stay out there? Well, if they don't, atoms will collapse. It would be terrible. Matter would collapse. All of you would be pinpoints long ago. Why? We're going to leave that to the next lecture. I would like to show you a model to illustrate alpha particles coming in to investigate, going into the inside of an atom and being bounced away by the positive charge on the nucleus. You see, if there is an atom with 1, 2, 3, 4, 5 electrons, the nucleus will have to have 1, 2, 3, 4, 5 electron charges to make a neutral atom. So it may be a very heavily charged atom if it's something, heavily charged nucleus if it's something as massive as a gold nucleus. I want to show you the experiment that Rutherford himself enjoyed doing very much in his own lectures. This represents an invading alpha particle. It's a tall pendulum from the ceiling, and this is going to be a very strong magnet pole. Underneath here is an electric magnet, an electromagnet. This is an ordinary permanent magnet, and I'm going to let this move towards there with a north pole here and a north pole here. See if they repel. Ooh, yes. See if they will bounce back. Pushed back, see? Ooh. Never mind the twisting. Now let's send it past and see if it'll move out that way. That's an alpha particle that came in, was repelled and bounced a bit off track. Of course, if we send it right off here, I'm going to run after it, it will go practically straight. If I send it right forwards here, hardly deflected at all. But now if I send it close and not so fast, a little bit of deflection, and now if I send it not so fast, big deflection. And of course this very big deflection backwards if you're careful enough with it. Woo! That was his illustration of his own theory, his own picture, his own thinking model of an atomic collision, a nuclear collision between the nucleus of a gold atom which he'd fired alpha particles through and a moving alpha particle. The experiments of firing alpha particles went on and on. They investigated the hollow space. They hurled electrons, tore electrons out of atoms, but presently they began to show other things. You could throw an alpha particle into a nucleus which took a special liking to it and said, come on in. It's like something in Red Riding Hood. Come on in, come along in, like that. And that alpha particle was never seen again. I'm going to show you presently models of that happening. But before I do, I have to tell you the strangest story of all, of alpha particles doing something very strange. Just casually, people tried shooting alpha particles at a rather light element. It's an element called beryllium. Beryllium is a light element, and they tried shooting alpha particles at it. They expected, possibly, to bounce the alpha particle in and change the nucleus. There's the nucleus of beryllium. But they didn't expect anything very extraordinary. And the alpha particle went in sometimes. Of course, sometimes it missed it like that. And another one might go in, and nothing came out visibly at all. No cloud chamber picture, just no sign at all. I'm going to put a very serious question mark here to say what is coming out. Perhaps nothing. But when they put some water or some wax, both are very rich in hydrogen, here they found something still more strange. Here's a layer of water, which will color a nice blue. There's water there. They found hydrogen atoms coming on from there. Who bounced those ahead? Supposing you're playing a game in the dark and some other child appears suddenly and is hurled in that direction, and you thought there was no one crossing the floor there. There was someone. Who were these people? They're invisible, and they're uncharged. They can't do any damage on the way. Very difficult to, at least. What are these things with no charge, entirely neutral, and yet able to hurl hydrogen atoms out when they meet that? What offers have I of a name for them? I only want the first letter. N. N. All right. What's the second letter? U. No one would choose U instead. It's quicker that way. All right. These are neutrons. They are the cloak and dagger people. They go in dark. They can be seen, they can go in unseen and do quite a lot of nuclear damage. We're going to see that happening in a moment. And when neutrons were first discovered, it once more changed the picture, because there'd been a worry about what was inside the nucleus. Here is once more the nuclear atom for you. I have to keep on drawing it for you. With the electrons, we still have to be very careful and just say there's no reason why the electrons shouldn't stay out there. They just do. The emperor has no clothes. Like that. Those are orbitses or something. There's the pattern. But what is there in the nucleus? What's it made of? There was plenty of experimental evidence that this is many times a hydrogen atom in weight or mass, so that it perhaps was made up of hydrogen atoms. Oh, yes, that's a nice idea, but it won't do. You'd have hydrogen atoms, all pluses, too many pluses. Well, perhaps there are some electrons there as well, in with them, to make some negatives, to enable you to put enough positives in. That won't work. We shall discover in next lecture that an electron is a very difficult fellow. He waves his way along, and he couldn't live inside the nucleus. He would be as you would be if you tried to live inside too small a barrel. He couldn't get in there. It won't work. And so there was a worry. The moment neutrons were discovered, it was easy, very easy. Hydrogen cores, hydrogen nuclei, which have a name. It's called a proton. The basic particle, hydrogen. There's hydrogen. The nucleus is called a proton. Protons are the red ones, and these are neutrons as well. And now we can match up the numbers and make sure it agrees with what you want to say in the book, and all is well once you put neutrons inside there. I'm going to show you a terrible-looking model which arises from that pattern. It's the model of uranium, of a heavy metal. There it is for you. It belongs to the Royal Institution. And it shows you black neutrons, red protons, and it's a very useful model for a certain reason that you'll see later. And it warns us that if this is just the nucleus, the rest of the electron part of the atom are out an enormous distance, a mile away, say, right down to Piccadilly Circus or further. And we'll come back to him presently. We'd like to show you, therefore, what neutrons can do. And we have asked Dr. Evans to get ready a demonstration of real neutrons for you with a real neutron counter. You'll find that whenever I move close to him, You see, moves me away. He takes some risk. How much risk is there?
As it is there, and as I'm this distance from it, no serious risk at all in the time that I'm here. But I wouldn't like to stay here indefinitely.
You'd not like to stay there all day?
All day would be all right, yes.
But not all day and all night?
Yes, but not all day and every day.
I see. Where is the source?
The source is in there. It's the metal cylinder in the tube there.
What's making the noise?
Oh, what's making the noise? That's a little detector that I carry here that tells me when things are getting a little bit too intense.
That's his warning signal.
It's merely to tell me when things are getting a little bit too close to me.
A lot more in his pocket than that.
Well, that one is what we call a pocket dose meter. It's about the size of a fountain pen, but it's a lot more complicated inside. It's a little ionization chamber, which you've seen, and in fact it is a gold leaf electroscope, made very small and also the sort that you can drop sometimes. That merely measures gamma radiation, and then besides that I have two other things. The blue one is what we call the film badge. It's photographic film and a lot of other things in the holder which tells me, or can tell me, how much gamma radiation I've had. And this one, which you haven't seen before, you've seen that one before, that one measures the neutron dose which I'm receiving. That again is photographic film, but used in a different way.
Dr. Evans has brought a neutron counting tube, which he will show you, and a register to show how many pulses he gets, how many neutrons the tube receives and measures. And this is a rate meter, how many counts in every second. There is the tube.
We'll park it in there
glass house.
just for safety. This is measuring, this meter here is measuring hundreds of counts per second. Full scale there is 100. Now if we bring the neutron source over, we'll put it alongside the counter and you can see whether we get any counts coming through.
Distance matters.
Distance and time are the things that matter. That is seeing actual counts, and that is seeing counts per second, and there isn't very much there.
73, 74, 75, 76, 77, very little. Why? Is it a poor counter?
It's a good counter for neutrons, but not the sort of neutrons that are coming out from that source.
There's a different sort?
Yes, these are fast neutrons, and if we can slow them down, we can get quite a different result.
How are you going to slow a neutron down? Let's think about that for a moment. A neutron is almost the same in mass or weight as a proton. There's a neutron, here's a proton of hydrogen. They're almost the same. And so if you let the neutron wander among hydrogen protons, he will go bang, bang, there's another proton to be there, and then bang to there, slower, 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 slower. In a path about between my fingers distance, he'll slow down quite a lot between one collision and the next. So we can put him in water. We've got a lot of water here. In fact, this whole tub is practically full. I'll just illustrate that by pouring in some more, but it's already 3/4 full. And we're going to use that to moderate the neutrons, which means to slow them down.
If you watch the meter, that doesn't mean anything. That's only a rocky cable. But as this goes into the water, you'll see a big difference on the meter.
There now. 8, 9, 10's gone off the scale. And this one, look at that. I can't read the rapid changes there of the counting. The tube is picking up neutrons successfully. It's a Geiger counter tube, essentially, a special counting device here, and we show with the slow neutrons, slowed by water, an enormously different story. Thank you. What have you next?
Well, the next thing is to show how we can absorb or shield from neutrons. You've seen before that lead works quite well. I've got a tube of lead here. It's quite substantial lead, as you can see. It's the same stuff, made into a tube simply because we're going to put the counter in there. So if we put the counter in that tube instead of this one, I can assure you there's no deception in this. There we have a lead shielded counter, and we'll bring the source back and see what happens there.
Neither better nor worse. The same failure as before with the fast neutrons. Try it in water. Look at that. As good as ever. Doesn't mind about the lead. Neutrons just bounce off the lead nuclei. They're good reflectors. They don't stop them, though. It's equivalent to having a dead person stand in the way when you want to get out of the room. You just bounce off him and move round. Just nothing happens. What have you next?
Let's try something different. Would you like to... Ooh, it got wet. Would you like to dry that? We've got
Yes.
to
This is a very thin sheet of cadmium metal, cadmium. And we're going to dry that and dry that. And then it'll fold into a tube.
Thank you. We'll wrap that round the counter. It's much thinner than the lead we were using, I hope you noticed. We'll waterproof it again by putting it inside a glass tube. Sorry, be with you in a moment. That's it. So now we've got the counter. Don't worry about the little bit at the bottom. That doesn't count anyway. Now we'll bring the source back in. Let's just
Same failure, fast neutrons, don't mind cadmium, nothing much happens. It doesn't slow them, not like water. Ah, now we've got something new. When the cadmium wasn't there, we went right up to 10 and we got fast counting. The cadmium has stopped a lot of the slow neutrons, slowed by the water collisions, which work this type of counter, which is sensitive to slow neutrons. And so we call the cadmium metal a moderator. It is called a moderator, which means a slower downer. Thank you. Now what next?
Well, we could do something with them, couldn't we?
You should. They're very clever creatures, neutrons. They can sneak right into the inside of an atom. Commandos.
There's a little piece of silver metal here, quite a small piece. We'll put that on this little tray. We're going to put this in the water in a minute. We've also got a cylinder here of silver, pure silver, with a little wire just to let us handle it. We'll put that in the middle of the tray. What we're going to do is make radioactive silver.
The silver is quite ordinary silver at present, just ordinary silver. Do you want to show it's ordinary? Oh,
well,
no.
we can,
This is
yes.
a small Geiger counter here.
Yes, it would be an idea, wouldn't it?
The good conjurer always opens his pockets first. That's just the normal background in this room. That's all right.
You want to see the little bit?
Hmm?
You want to see the little bit? Right. Now what we'll do is put the source right in the middle of that little cylinder, and both bits will get a certain amount of neutron radiation.
Some of the counts you hear there are from a different radiation from the source. There's some gamma radiation from it, which go right across the space there to the counter.
Now, fast neutrons don't do anything very much, so we'll put it right in the middle here and
It's well in water,
deep down.
in among a beehive full of bees, which are not bees but slow neutrons, staggering about slower and slower, and then attacking the silver and making a radioactive set of atoms. Dr. Evans will give it a minute or two there to brew, so to speak, to collect up enough to make enough silver atoms that are radioactive to show here, so that meanwhile I'm going on with the story with you because he will need a little time there. We could use that silver for rubbing one piece on another and show how friction drags atoms off. We could use radioactive sodium as a tracer to trace in your blood system. We can make lots of uses of artificially made radioactive materials. I'm going, therefore, to get ready to show you a model of radioactive changes. I have 3 large boxes which will come in while we're waiting for the silver. We won't use them until we've had the silver experiment. Thank you. One box I shall use as an imaginary nucleus of gold, and I shall approach the nucleus of gold with an alpha particle. This is an alpha particle, which is just a helium nucleus, doubly charged, and it's going to go crash into this nucleus, and you'll see what will happen. It. Wait now. You wait now. No, we'll leave it like that for a minute. How's it getting on?
Would you like to try this?
Yes, please. We're ready to try the silver. The little clicks are just from the gamma rays from the source, which emits a few as well as neutrons. When we put it home, you won't hear those so much. I'll take the big lot of silver and put it there. Can you hear it? Now, Dr. Evans, leave it there, and you'll hear whether it has a long half-life or a short one. Good. Thank you very much. I shall feel easier in my mind if you've taken the neutron source out. It goes out into a special store of safety. Thank you, thank you. This is a very simple model without any label on it. It might be a gold nucleus, we don't know or mind. Ah. How's the silver getting on? Going down or staying the same? Very short half-life. This is what an alpha particle does when it approaches a gold nucleus. Or a still slower one just does that. Or a fast one just does that. Bounces back. That's all that happens. It never gets right up into the nucleus. That would be very difficult for it. The repulsion is too big, and so the hill is never used. We'll take that one away. The next model is a model of alpha particle into a beryllium nucleus, and that is quite a different matter. You may see something happen. This is difficult to do even with our model. I'm going to try to roll it in. You notice there's a label on the nucleus saying beryllium. How's the silver getting on? Less? It's a very short half-life of a minute or minute and a bit. Now I'm going to roll in this and see what happened. That often happens. It misses. It's very common for that to happen because it's not easy to get something sneaking into a nucleus. That's all right, it bounced back. That's all right, it didn't bounce. That one was not operative. Let's see if we can do something more operative. I'm going to put it right in by hand, be sure. The beryllium nucleus did not wish to emit a neutron. It turned temperamental. It can happen, I believe, with real beryllium. This we hoped would emit a neutron. I will have to therefore fake the story for you. Suppose a neutron has come out of the nucleus like that. There's an immediate change of chemistry to a carbon nucleus, and out comes a neutron, which I'm going to use for the next experiment. Here I'm going to throw a neutron into an atom of quite a different element, of aluminium, and we'll see what will happen. I had hoped to show you that out of that would come a red proton, and so I'm going to illustrate it just by what might happen, and when it does, at once it changes, leaving a magnesium nucleus there. And now we are left with a magnesium-excited nucleus which may decay at any time, we can't tell, and may emit some particle. We have to wait for some time, which is not far from a half-life for it or something of that kind. Just watch. May happen. There now, an electron, and a high-speed electron too. And the wretched thing goes back to the aluminium again. There's also a gamma ray which may come out at the same time. Now the strangest thing of all. The strangest thing of all is when a neutron goes into a certain form of uranium nucleus. There are two brands of uranium. The common one, many of the atoms are of relative mass 238, a few are of relative mass 235, and it's this one. When a neutron goes into that, it's swallowed up, and it becomes very unstable, and in the end the two halves fly apart. The flying apart is called fission. We're going to show you a very crude model of fission just for fun. I'm slightly nervous about it. It's a very unstable model. There it is. Now at present it's equipped with a safety control rod. Take out the control rod on your side. Hold it steady, let go. I'm going to pull on my side. I'm going to pull. Yes, yes. I don't want it to... Oh! I'm sorry, it blew up before the neutron got in. But look, there are lots of spare neutrons. And that's the important thing, that when a uranium atom splits into two pieces, releasing an enormous amount of energy, here's the energy, an enormous amount of energy. I'll give you back the energy that you own. Enormous quantity of energy released. The two halves fly apart with positive charges on each, repelling and driving apart, delivering an enormous quantity of energy and releasing spare neutrons. Therefore, one uranium can trigger other atoms blowing up in turn and make, or what you call it, when one event triggers another and those trigger others and others. What's the name? Chain reaction. Good, you've heard it. Remember, in one generation ago, it was an word except in technical science. A chain reaction. I'd like to illustrate that by showing you two kinds of chain reaction with matches. We have here a row of matches. This is what you would call a controlled, steady chain reaction. It's the old principle of a fire. In a fire, one carbon atom burning delivers enough chemical potential energy to the next carbon atom to make it burn with appropriate oxygen, and on and on and on in a chain reaction. I hope to show you a chain reaction here. This is a continuous chain reaction, a controlled one. This is what is used with uranium in a reactor for a power station. There's an old name for the chain reaction going down these matches. It's called a fuse. And at the end, there is an explosive chain reaction. And that is what happens in a uranium or plutonium atomic bomb. You may be sorry if I talk to you now and again, perhaps in the next lecture, about atomic bombs. But if you don't understand about those dangers, and you don't understand how it works and what happens, you will find it quite a nuisance to understand anything about a nuclear reactor for power stations. And if you don't like nuclear power stations, you still ought to know enough about them to be able to argue against them violently. That's the bomb. I hope that my colleague who prepared those matches and who told me it took 6 hours was there to watch it on television. I have now a model which has come to us from France. Want it like that? You will see this up on the monitors. This has come from the great Paris Palace of Discovery, which has a very beautiful exhibition of nuclear science. I should say probably the best in the world. It's remarkably good. And they have here this particular illustration of neutrons hitting uranium nuclei. These 6, 7 things are uranium nuclei. You can see they've got a complicated structure, and neutrons are going to come in and hit them. Ready? Watch. It's a neutron. Fission. One fission and one lost. More fissions. More fissions. That's the end of it. Want to see it again? I got it from Paris through the customs without saying what it was. If you go to the Paris exhibition, you'll see other ones like that. So I think you need to know what happens in a bomb and certain things about it, and then what happens in a power station. We shall have an enormous model at the next lecture of a nuclear reactor for a power station. But I'm going to talk about the problem of a bomb, however much you dislike it. This is necessary knowledge. It's equivalent to necessary medical knowledge. All educated people, as they grow up, should learn quite a lot about their bodies and how they work and what happens when they're ill. Because otherwise, the doctor can't help you so much, and you might easily hurt other people very much indeed. So suppose we have a small block of uranium here, and we fire into the small block of uranium 1 neutron. I'm going to fire a neutron in, like that, just one. Oh, they come in all the time from outer space. Every one of you, been struck, pierced through by a neutron sometime during this lecture time. Quite harmless. If it goes straight through, nothing happens to you. If it stops, well, a little tiny few ions made. 1 neutron won't hurt you, and you've always lived with it. In comes the neutron, and it starts a fission. By luck, it hits a uranium-235, and the fission drives apart like that, heating up the block, of course, and releasing a couple of neutrons. This was the great secret in the Second World War. How many neutrons from one fission of U-235 single nucleus? The answer was kept secret. We were only told it was a number between 1 and 3. Oh, no, you're wrong. It's more than 2. Between 2 and 2.5. So that out come a couple of neutrons like that. And where will they go? They are dark, sneak-rayed creatures. They can bounce through anything easily except cadmium. And so out they come. They're lost. Of course, what you hoped was that the neutron, as you saw in the model, would start another fission here, hit something, and then out would come more neutrons from that, like this. But that won't happen. They chiefly escape. How can we stop neutron escapes? Very simple, very expensive. Build more strong uranium barrier all round it to catch them. Here it is, here it is, here it is, here it is. And then you have something which is more than critical size. If it's more than critical size, more than necessary to collect neutrons, what will happen? Do you know what will happen? There'll be bang, 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 heat, 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 heat. The whole show, even if you thought it was a reactor for a power station, will blow up or crack with heat. You don't want that to happen. So you will have to put in something at the last moment for safety. What are you going to put in for safety? I'm going to show you. It's a rod which goes in for safety. What's it made of? Guesses? Thank you. Cadmium will do. There are alternatives as well. The army used to ask in the old days of starting this for a small bomb. You can't have a small one. You can only have a big one. And what you have to do is to build a big bomb, bigger than critical size, but then put control rods or something between it here control rods to keep it safe, and pull them out at the last moment, and then you've got a critical size, and up it blows. We have, in conclusion, a special nuclear bomb exhibit for you. I'm going to represent uranium-235 atoms by a mousetrap. You see, you can set this little mousetrap like this. It bites. Not the mouse, but the trap. You can set the trap, and when you have set it, you can get from it quite a lot of energy, about 1 joule per mousetrap. We can load it with these 2 red corks, which represent, you see, it's very sensitive, represent neutrons. But suppose I did load it successfully, then what would happen would just be this, that I should bring an extra neutron from some other neighboring nucleus here. Look what happens. And they're lost again. You need an assembly of mousetraps of critical size, or a little bigger. And we have one. No. In this, if one mousetrap is hit, it will throw out a couple of neutrons. There's a neutron reflector all the way around here. They'll bounce back. They've got quite a big capture cross-section, which is the cheese plate on which they fall. And so we have every hope of your seeing a chain reaction as a model of a bomb. But when we can control it, it's a model of a power station. Are you ready?